thanks, Yunsi, for the introduction. I hope you can also hear me online now. It's my pleasure to also kick off the technical part of the 9th Open Sky Symposium. As Yunsi said, in my and actually all of the founders of Open Sky day jobs, we used to do and still do a lot of security and privacy work. So throughout all of the symposiums, most of the things we've presented is typically on this. It's very nice to see that the topics have broadened a lot, but we are still here and we're still talking about ADSB, security and privacy things. This particular project was done with data pre-COVID with 3 students from ETH Zurich in a data science lab. And it is extending some work we've done previously on tracking aircraft of interest, in particular corporate and state aircraft. And we are now looking further into this. Rather than doing only historical tracking, we try to extend this into the future, but I'll show you what this is about. First, let's look at the motivation. You know this picture, and obviously there are a lot of other aviation data providers. And as we know, aircraft are now in real time globally trackable by anyone. This doesn't only include commercial aircraft, it includes a lot of interesting stakeholders such as military aircraft, corporate aircraft, and government aircraft as well. How do we go about tracking an aircraft continuously? Well, the key identifier here has always been the 24-bit address assigned and typically unique for every aircraft transponder. It is a much better idea or way to track aircraft than, say, the call sign or the registration, because it's well defined, has certain ranges, and it's less of a risk of errors being introduced during the reception process, also of ADSB sensors. So it's really great for analysis and automation of air traffic tracking. The other thing that we, however, need is actually some information about what aircraft is this, who is this. So we need metadata. There are many databases out there. We also have our own database within Open Sky, which currently tracks 520,000 airframes in there. It's crowdsourced, so anybody can help us with this and improve it. But currently, I checked, and typically it covers 92–94% of the currently seen aircraft. So just as a background, that's what we use. And if you do that, and as I've mentioned, we've been doing this for several years now, you can track, for example, government aircraft. This picture was made based on a list of around 500 government aircraft of roughly 100 countries around the world. And it shows foreign governments, so non-European governments traveling into Europe in this case. Not very surprisingly, you find a lot of hotspots, London, Paris, well, so in Switzerland, Zurich, Geneva, and last but not least, here in Brussels. As you would expect for a lot of meetings between governments, you have the government aircraft come in. Likewise, in this case, we see Zurich Airport for the World Economic Forum. And with good coverage, you can track all of these aircraft down to the runway, as we can see here. So within 1 or 2 days of a certain event, you would see all these aircraft come in, and obviously you see something is happening. You can automate this, you can cluster them. It is interesting. It has some effects beyond academics. This is a well-known case where some journalists in Geneva set up a simple ADSB-based bot tweeting out certain aircraft from certain governments. Just going and departing Geneva Airport. And this was mentioned in certain proceedings. In this particular case with the Vice President of Equatorial Guinea, it is possible to track certain people, certain members, and actually act upon this. So this is but one example. I am sure there's a lot more that is also not being publicized. Likewise, government military aircraft are not the only affected stakeholders. We did this analysis back then with corporate aircraft. We looked into mergers and acquisitions activity, looking into 7 cases where OpenSky at the time had good coverage and where we could identify mergers and acquisitions between companies that were using and where we could identify the corporate aircraft. As you can see here, in 6 of the 7 cases, there was a good signal where, like, the buyer of one corporation went to the target's headquarters and close by. So within sometimes a week before the merger announcement or within the month before. We can look a little bit more closely into one specific case that we have here. This is Basel Airport and the headquarters of the pharma company Actelion. And we see a certain corporate aircraft coming in here very often over a short period of time. We zoom in a bit further, we again see the dates when the corporate aircraft here landed on the runway. And you can really follow the whole procedure like in real time. So you can see here, 26th of January, 2017, at 7:57 in the morning, this aircraft landed. And an hour and a half later, it was announced that US company Johnson & Johnson would buy this Swiss biotech firm for a substantial sum. There was, of course, some stock market movements on these announcements. So if you knew this in advance and just this 1.5 hours in advance, you could act before this announcement. You can follow the whole thing even further. As you may be aware, takeovers like this take some time. They have to go through with regulators. So there were more flights after the announcement. In this case, 2 on 15th of June and 16th of June. And indeed, again, another stock market moving announcement when the acquisition was actually completed and approved by the regulator. After we published on this, people certainly picked up on that. I'm sure hedge funds were already doing this before with available aircraft data, but there were several articles since where this sort of signal has certainly been incorporated into hedge funds models. So as you may imagine, or as we have seen, it's certainly useful to get this data both historically for analysis, but also in real time to act upon it. But what if you could get even a better advantage over the others who are doing this now as well, and you try to predict in advance if an aircraft is in the air, where it will land? There's a lot of research trying to predict, also for purpose of air traffic management, where an aircraft will go within the next minute, the next 5 minutes in the air. But there's very little actually trying to predict where an aircraft goes, probably because at least for a lot of the relevant stakeholders, they would have access maybe to flight plans and they would know where it goes. But that's not necessarily the case for a lot of the aircraft we're looking at here. And for a lot of the actors who are interested in this data, they may also not have it. The only thing they have is the live or historical ADS-B data. So as happens so often with these machine learning approaches, most of the work goes into basic data cleaning. We have heard often we have had a lot of talks about this at prior Open Sky symposiums, and things also have gotten much easier with certain libraries that are now available also for Open Sky data. But in principle, it's always the same. You take the flights, and here you have always the question, what constitutes a flight? We've actually seen it, similar approaches and questions earlier in the keynote. It's both a technical and sometimes a philosophical question, but Open Sky's approach, we actually finally formalized and published it recently in a paper, so you can look at that in the reference. If you take the flights from Open Sky and then just take one data point per minute is sufficient, because if you look at a lot of data as you need here for a machine learning model, you want to tone down the granularity, of course, quite a bit. You have to do a little bit more cleaning. Obviously, there's always some outliers caused by a lot of different issues, and smooth it over by computing the missing values. The second thing that you have to do with that data is really to label the flights, and in particular, both the origins, but in particular for our case, the destinations. Again, Open Sky has an approach. So if you use our website and the Impala shell, you will find a lot of flights being automatically labeled where possible, according to what we think their destinations and their origins were. We refined it a little bit just for this machine learning approach here. 3 zones, essentially. If the last known point of the aircraft trajectory that we got is above 5,000 meters, we just assume, well, it left coverage of Open Sky, and we simply don't know where it's going. Like, you cannot actually derive any information from that. If it's between 1,500 and 5,000 meters, we basically take the first order approximation, where it's going based on heading and speed, and then look at the nearest airport and use that as our ground truth here. If it's already below 1,500 meters, we probably get a pretty good idea where it's going to land. We also do this not particularly sophisticated fashion. It's still looking at the nearest airport and not incorporating any information on the basic approach trajectories on specific airports. And if you just looked at heading at this point, when there's a lot of turning going on, that didn't actually turn out to be a better approach than just looking for the nearest airport in this zone. The second thing we needed to do for this approach, or we wanted to do really, we had to create some airport clusters just to see how good can our granularity become. That means we cluster things. We used weighted k-means clustering here and did some obviously manual checking, so not to exclude like airports such as Reykjavik here. But in principle, the question is 10, 15, 100 airports clustered together. How good can your prediction become if you predict the aircraft going to one of these clusters? Finally, the basic feature engineering was taking, as I said, the metadata of the aircraft, so type and operator. Then you need the time of the day and the weekday and the origin. And from the trajectory, as I said, we originally had the granularity of 1 data point per minute, but for the final modeling, for the prediction of an aircraft, we realized it's absolutely sufficient if we take 10 samples per flight randomly or equally spaced between the origin and the last point of interest. The model, in this case, also very simple, no no fancy deep learning or anything. So we just used the random forest model, 200 trees and balanced class weights. The results, everything here is pretty much still work in progress, but they're quite encouraging. So for the three different stakeholder times that we looked at, business jets, government jets, military aircraft, you can see that around 20-25 minutes before landing, you have a very good idea where it's going. This is not very surprising. If you look at it, you will probably see it. But we can see that in particular for the government and the military aircraft, the model knows even 1 hour, 2 hours, 3 hours before where it's going in many cases. There are obviously a lot of explanations for some of this. If, say, a German Air Force aircraft has only a certain number of bases where it's coming from, where it's going to, in most cases. So there you learn a lot about from the background and the operator and the type. For governments, they also, as you've seen, they tend to go to a number of hotspots very often. But it's, as you can see, it works fairly well. Business aircraft, the granularity, and in particular, I think the variance of the different corporations, where they come from, where they go to, is much higher. So we lose a lot of information after about an hour of this. Even then, it's much better than random guessing. You can often get a very good idea. I was talking about the granularity of the clusters. Obviously, if you cluster more airports together, the model should work better. So if you only have 10 clusters in Europe and North America here, it performs the best. Also, the information is quite low, but actually you don't lose a lot of information if you go down to 100 or 150 clusters and group fewer airports together. So we're quite surprised that the granularity there works quite well, even with 750 clusters and very few airports per cluster. What can you do about this is certainly in some cases an interesting question. We've seen military aircraft, government aircraft sometimes switch off their transponders. This is a standard operating procedure for many of them. They use it where it's needed during cruise, but then at least ADS-B is being switched off during start and landing. That can help a bit. However, if you use multi-iteration or other means of information, if you have access to that, it is actually not that effective. Clearly, you could use commercial transport, but as has been pointed out quite often, that might actually be on the internet quicker than just following an aircraft. So in this case, I'm not sure how much that helps, but at least chartering a jet that is being shared with somebody else would help, I think, a lot of people that they cannot be tracked in the long run. Mitigation we've been thinking about. It's a bit esoteric, but could you change your flight pattern just ever so slightly? Like if you leave from an airport and you take just a slightly different route, can you throw off the model? This seems very likely. We haven't checked it yet. You could even think about poisoning the training data. So if you want to go to an airport undetected, you could have a bunch of flights beforehand that do something else, and then you do that. Clearly, there are some trade-offs with operational needs. So it's more of an academic question, and it would have to be really worth it for you to go out of your way, literally, to do this. But I think it's still academically an interesting question. Few limitations just to come to the end. It's machine learning, it's proof of concept. So there's a lot of things to do here. You can always improve, as a lot of people are doing here. on encoding of flights and trajectories, looking at interesting airports specifically. You could separate actually the models for each of the subtypes to get a better understanding. We just use one model for all of them. We can use more flight data than just 1 year, which we used here. We can include contextual data, whether we can use deep learning algorithms. So a lot of things that could be done there. Yeah, what do we learn from this? We know there's almost no privacy in the air. Aircraft can and are being tracked in automated and global fashion. That is useful for a lot of things. That's why we're here. From security and privacy point of view, it can sometimes be problematic for operational security, and a lot of stakeholders are being affected by this. We show that you can actually predict where you go before you land, half an hour in advance or an hour in advance, with relatively simple means, which can be improved. And with some of the aircraft of interest, as I said, you can even do this quite long in advance. Yeah, I'm over my time here, so I'm happy to take questions on this. Thanks.